In this lesson, we're going to be looking at trigonometric identities, and we're going to be looking at them with an expanded view of potential identities as we've been exploring in our previous lessons, where we looked at compound angle formulas and the double angle formulas. Some people really enjoy trigonometric identities. They enjoy the puzzle aspect of solving trig identities. Some people find them quite difficult. One of the reasons why is because with trig identities there is not a single correct way to do these. There is a certain amount of trial and error, there is a certain amount of intuition involved in getting the correct answer, particularly when you're dealing with getting your skills developed to the point where you can do this quickly. I'm not going to say easily, but directly. Now, although I say that there is a certain amount of intuition, you can develop this. It's just there's no formula. There is no set of steps that is going to get you there every time. Or the steps are so general and you still have a lot of choices to make yourself as to how to make those steps move forward. Quick note here, when we talk about doing proofs in general in mathematics, not necessarily just trigonometric identities, proofs are actually a lot harder to do than a counterproof or a disproof. Because a proof is saying that this is true for all conditions that are listed, and usually in our case we're talking about all valid values for the functions, sine, cosine, tangent, and their reciprocals. Interestingly though, in mathematics, a single counterexample is all it takes in order to disprove any particular example. So if you've been asked to disprove something, you could just go ahead and substitute in a valid value. It has to be valid. You can't choose things like values of asymptotes, for example. But if you just choose a regular old value that you know will be valid for all of the trigonometric expressions involved, and you don't get left side equals right side, then you have basically disproved that particular identity. So that was just a bit of an aside note. You're probably not going to be asked to do that very often, if at all, but it is something to keep in mind when you're talking about mathematical proofs. So these are just some tips. If you follow these, if you work at developing these for yourself, I think you'll find that your work with trigonometric identities will get simpler, will get more efficient, and maybe even a little bit more enjoyable once you start to develop a better idea of how to progress forward. You are dealing with mathematical puzzles. There are rules that have to be followed, as is the case with most puzzles. But once you get a good grasp of those rules, things will go more smoothly. Now, the first thing I want to advise you is to keep your goal in mind. When you are doing a trigonometric identity, you're going to be working on one side, the left side or the right side. But you need to keep referring back to the other side because you're trying to get from where you're standing to where you want to go, and you're going to need to make sure you're closing in on that target. If at all possible, start with the most complicated side and then try to make it simpler. If you start to make a side more complicated, that may be a hint that you need to go look at the other side. Try not to bounce around between the two sides. Pick a side and stick with it until you feel like you've really exhausted any progress that you can make on that side. I don't want people to automatically go to my third piece of advice here, which is if you're stuck, try expressing in terms of sine and cosine. I do say if you are stuck. Oh, there we go. And unfortunately I'm stuck because my pen is not responding here. There we go. Okay, so if you are stuck, try expressing in terms of sine and cosine. And that's just because if you write everything in terms of sine and cosine, you may end up with an algebraically more difficult expression. But once you're down to sines and cosines, the only identities you're going to be dealing with then are pretty much the Pythagorean identity. Now this will probably only work if you are working with both sides that way, unless you happen to have one side is equal to a constant, or maybe you have one side that's already equal to sine or cosine. Anyway, these are not things you commit to memory. These are things that you will start to get a feel for as you work through these. And I know it's a pretty common message in mathematics, but the more of these things you do, the better you should become at it. It's not a guarantee, but it's the best way that we know of to make progress in this way. Now, in this case, I'm going to start off with actually what appears to be a fairly complicated identity, one that is not immediately obvious. What side should I start with? Now, in this case, I'm going to start with the left side, and the reason I'm going to do that is because at the very least, the left side gives me something that I can work with. I know how to move directly from cos x minus y and cos x plus y to something else. When I look at the right side, I see 1 plus tan x tan y and 1 minus tan x tan y. There's something reminiscent there about the compound angle formulas for tangent, but I'm missing a pretty big part of that. So this is the denominator from one of those, and this is the denominator from the other one. So rather than trying to figure that out, I'm actually going to go the other way here. So I'm just going to say the left side is equal to the cosine of x minus y over the cosine of x plus y. And I cannot stress this enough. You must work the two sides independently of each other. So you can't keep this equation intact. And one of the reasons for that is because you might start getting tempted to do things like cross multiply, multiplying both left side and right side by the same terms. But you can't do that. And the reason why you can't do that, algebraically, one of the most important concepts in proof is something called reversibility. And the idea that I can go seamlessly from this left side and transform it into that right side. I'm going to show you an example of that a little bit later. So start with the left side. Cos of x minus y, that's the cosine x cosine y, minus here becomes plus here, sine x sine y, over cos of x plus y is the cosine of x, the cosine of y. This plus becomes a minus, sine x sine y. Now I take a look at this and I compare it, even if you just glance, but I'm going to be a little bit more deliberate about it here. I look back at my right side. Cos x cos y sine x sine y. I've got tan x tan y. So that actually, I've at least got this idea of multiplying different ratios, one with x and one with y. Now the next thing you might ask yourself is, well, how do I move from this left side to this right side? And perhaps you see that, or perhaps you don't. And if you don't see that, well, that's okay, because what I want to do, just to illustrate my point here, although I can see how to move forward here towards this right side, I'm going to just pretend that I don't. And so I'm going to say, okay, I've come as far as I can here, but I don't see the path forward, or I don't see a way that I can change this that won't make the whole thing more complicated. So now I'm going to go to the right side, which is 1 plus tan x tan y over 1 minus tan x tan y. And that is equal to, now I'm going to change, well, tan and tan x tan y, I don't have a good transformation there other than to use the fundamental definition of tan, which is sine x over cos x and sine y over cos y. That's all in the numerator. Be really careful once you start to get fractions over fractions. Make sure your equal sign lines up with this main division line. Even if you have to redraw it if you've got a problem with your scaling, it's still a better thing to do it that way. Sine x over cos x here, sine y over cos y here. So now I go ahead and I give myself a little bit more room here. So I end up with 1 plus sine x sine y cos x cos y. So what I'm going to do is take this numerator and give it a common denominator of cos x cos y. So I'm going to make my division sign a little bit, actually I think I'm going to have to stretch everything out a bit here. So what do I have to multiply 1 by to give it a denominator of cos x cos y? Well, that's just going to be cos x cos y. And then this already has the denominator of cos x cos y, so that becomes sine x sine y over cos x cos y. And the thing I'd point out here is you still want to, now that I switched to the right side, I want to take a look at my endpoint of the left side and see if I'm moving towards it. And that was just a big step that I took there. Because now I've got cos x cos y, sine x sine y, but I've got this cos x cos y in the bottom. That's going to be a problem, but not for very much longer. In the denominator, I'm also going to have a common denominator of cos x cos y. And this 1 is going to become cos x cos y, and it's going to be minus sine x sine y. I have a fraction over another fraction. So I've got a over b divided by c over d, and that's the same as a over b multiplied by the reciprocal of the second fraction, d over c. And so in this case, what we end up with is cos x cos y, this is the numerator's numerator, plus sine x sine y, divided by cos x cos y. And then I'm going to take this part and I'm going to take the reciprocal of that. So that's going to become times cos x cos y over cos x cos y minus sine x sine y. And at this point, I've got, this is all multiplied, and you need to understand that's multiplied in a bracket like that. So I've got something times something times something. And so long as I don't go into this bracket with any divisions, then I'm fine. So this bracket preserves the addition here. This bracket preserves the subtraction. But otherwise, I just have multiplication and division. Cos x goes into cos x one time. Cos y goes into cos y one time. And my result of that is I've got this bracket, which is cos x cos y plus sine x sine y over cos x cos y minus sine x sine y. And you can see that that is the same. So now we have left side equals right side, and we have proven the identity is correct. Now the next thing I want to do is I want to look at this identity again, and I want to look at it in the context of this idea of reversibility, which is the idea of a one-sided proof where we're going to turn the left side into the right side or the right side into the left side. Now before I do that, since I'm not really doing anything new, just thought I'd post, here's the homework associated with this lesson. So you can get started on that if you're ready to. And now I'm just going to pursue this out of some interest that people might have, just understanding this idea of the term reversibility. I'm going to do exactly what I did before, which is I'm going to start with this left side, and so that's going to be cos x cos y plus sine x sine y. It's not actually that much more to do. Cos x cos y minus sine x sine y. Now I take a look and I see, well, I would like tangent here. I've got sine x. I even have the right number of terms. I've got a term plus another term. I've got a term plus another term. But I don't have a 1 here. I have a cos x cos y. Well, how do I turn a cos x cos y into a 1? That's one first question you should ask yourself. Perhaps a more important question is, how do I turn sine x sine y into a tan x tan y? Well, that would be best if they were over cos x cos y. And another way of, when we talk about getting something over some value, so I'm going to show you two ways to represent this. One of them is a little bit more elegant mathematically, a little bit more insightful. But the cruder way to do this, in my mind, but it's still valid. I don't want to, when I say cruder, I don't want to somehow disparage this as a technique. It's perfectly fine. I know I want this over cos x and I want this over cos y. So what I'm going to do is I'm going to multiply this whole numerator by cos x cos y. But I can't just make this appear out of thin air. I have to multiply the denominator by cos x cos y. Sorry, 1 over cos x cos y. And of course this whole fraction is the same as this whole fraction, which means they divide out, and all I've really done is multiply by 1. And if I do that, I'm going to accomplish what I was hoping for there, which is I'll have cos x cos y divided by cos x cos y, and I'll have sine x sine y divided by cos x cos y, turning it into tan. And if you go ahead and complete that algebra, you're going to end up with what we were looking for here. But I'm going to take a slightly more, what I consider to be a mathematically elegant or insightful approach, which is I'm going to factor. How do I turn cos x cos y into 1? Well, I'm going to, in the numerator, I'm going to factor out cos x cos y, which is really, there's obviously a very strong connection between factoring and division. So when I take out a cos x cos y, what remains here? That remains a 1, because if I reverse this, cos x cos y times 1 gives me cos x cos y. When I factor out a cos x cos y from here, it's like I've divided by cos x cos y. So sine x, when I factor out, if I have sine x and I factor out a cos x, that's the same as sine x over cos x. But I can go straight to writing this as tan x. So that's the same thing I'm going to do here, is I'm going to factor out a cos x from here, turning that into a tan x. I'm going to factor out a cos x from here, turning that into a tan y. You know what, I'm just, rather than taking that shortcut approach, let's go ahead and write it out the long way, which is this would be 1 plus sine x over cos x sine y over cos y, all divided by and over here I'm going to factor out cos x cos y, and now I get 1 minus sine x sine y over cos x cos y. And of course cos x divides out with cos x, giving me 1 and 1. Cos y divides out with cos y, giving me 1 and 1. And this simply becomes 1 plus sine x over cos x is tan x, sine y over cos y is tan y, over 1 minus tan x tan y. And the left side is equal to right side, the only difference being in this case I didn't actually change the right side at all. So what I've done here is something that's completely reversible. I should be able to work forwards and backwards through this, because this is the right side. I've gone from the left side down to the right side. I could go from the right side back to the left side by reversing those operations. And once again, back to the assigned work. And obviously that previous example, it's only relevant in the sense that to have you thinking about this idea of reversibility, and also making you aware that if someone wants you to work entirely on one side, you can still do the work on both sides, because when you get to the point where you've shown it to be true, for example here, which we did on the other side, you should be able to then step yourself back. You should be able to step yourself back one step at a time until you end up back at the starting point, in which case you've done a one-sided proof. And then you would just write that out all on one side. Okay, that's it for this one. A bit of a digression, but hopefully me popping in that homework earlier got some people started who are really keen to get going.